Assalamualaikum and hi to my students. Welcome to the video lecture of a new chapter, Chapter 5, Abstract Algebra. It can be broken down into several sections, and we will start for the introduction of group and we proceed with another group structure. But for this video lecture, I will emphasize on the basic characteristic of group. Abstract algebra is a field of pure mathematics that concentrates on the structure of algebra. There are various structures of algebra. For the smallest one will be monoid that we will learn, and the largest one will be the field. But group consists of several characteristics. Let's start first with the fundamentals of binary operation. I teach you first how to read the structure of group. Let a group be defined, a group G. For example, I want my group to be consist of this integer, and I put binary operation. We recall back from chapter 2, Cartesian product. There is a binary set, ordered pairs, because it involves two elements. Right now, there is also a binary operation. For example, I put plus. This representation of G is actually means the addition of integers. That is how we define G. This G can be various. The binary operation is also plenty. For example, this is the first one. I can also say the subtraction of integer, or even the multiplication of integer. There is also another type of set which is known as Z integer modulo n, and it can be many binary operation that is associated with it. There is also UN, stands for the integer which is pairwise relatively prime modulo n, and you will find many more kinds of set which has been highlighted by Dr. Sham here, but I will try to focus only on the concept which involves integers, because discrete mathematics concern more on integers. However, if you learn abstract algebra, it can also involve rational number, and also, why not, a real number as well. As a summary for this G, the first element on the left is a set or a domain. The right one is the binary operation. That is how we define G. Why we call it a binary operation of a given set? If you recall, it is easy to add up integers. I let 1 to be my integer, 2, and the binary operation is plus addition. When you try to add up the element, it always involves two elements at one time. Becomes another thing, 3 here. If you try to add up 3 integers, 1 plus 2 plus 5, in a normal operation, we always add up the first two, then you get the next binary operation, it will become 8. You can also do this associatively like this. You add up the right one first, it becomes 1 plus 7, eventually it becomes 8 as well. In a nutshell, it means that every operation always stems back by the inclusion of exactly 2 elements at one time. Just now, I mentioned the word associative. A group, let a group G, G not necessarily must be a group. To verify whether it is a group or not, it must satisfy 4 properties. The first one, which is mentioned in the top sentence of the definition there, it must be closed. Closed means that for every 2 elements in the given set of G, a binary operation with B will produce, for example, C. This C must also be an element of G. That is the meaning of closure. Later I will apply it in the addition of integer. Let me finish with the associativity first. Associative, it means that for every 3 elements in a given G, A in the bracket B, then you do with C will be equivalent if you do B and C first. For the third one, identity, the keyword is that there exists some element of E which is also an element of G such that it behaves this way. A binary operation of let me write back carefully to be consistent. For every element of A in G, there exists some element of E which is also an element of G which behave this way. A binary operation E is equal to E binary operation of A. You will get back A. That is the meaning of identity. You get back the original value of A. And the last one is about the inverse. For every A in G, there exists its inverse, a unique inverse, exists uniquely. For example, B, okay, such that AB is equivalent with BA, you get back E. Therefore, E, identity and also inverse is closely related. If we have identity in the G, in the group, then there will exist inverse perhaps. You need to check first. But if you don't have identity, therefore directly you don't have inverse, guaranteed, because you cannot equate AB binary operation which equals to BA equals to E. Later we will see the examples. If any given sometimes for the inverse part, I sometimes like to write like this: inverse as A inverse the power of -1. Sometimes, not sometimes, I always use A to the power of -1 stands for the inverse. I seldom use B, but actually it's the same, just the representation is different. If any given G satisfy the 4 keywords: closed, associative, identity, inverse, if satisfy all of the properties, then we can say that the G is group. If it fails at least one of the properties, then it is not group. For example, if it satisfies closed associative identity but it does not have inverse for every A in the given G, definitely not a group. Therefore, you must always check for 4 characteristics that needs to be satisfied. But in the question, I will always ask like this: prove that a given G prove that a given G is a group by checking all properties of the group. Sometimes my student, for example, I give a question, they found out that it is closed but it is not associative. Then they directly skip number 3 and number 4. They say G is not a group. Technically the student is correct, but the question will always say by checking all properties. If you find that kind of instruction, you cannot skip identity and inverse. You must try to prove or disprove whether the identity or inverse exists as well. Please do take note on that kind of instruction. Let's try to do the first example. The problem there is not much solution in the slide because the solution is usually long. That's why my friend does not include full solution in the slide. That's why I try to show it during this video lecture. And perhaps if we do have time for face-to-face, then we do this face-to-face in the future. But that's in the future. Let's talk current. Proof atau determine. Determine whether G given by addition of integer is a group. Again, by checking all the properties of a group. We start first with the closure. And I purposely put the notation on the definition of a group on the left so that you will recall the left and right at the same time. The closure means that for every A and B in the given G, the binary operation between A and B will produce some C. That C will be an element of the G as well. How to apply it in the addition of integer? For every A, B, which is the domain integer, you need to check whether A binary operation with B will produce something which is a member of the integer as well. This is how it goes. For every AB, which is an integer, it will be the binary operation plus B will be equivalent to C, for example. Let's imagine this. If integer plus integer, integer A plus integer B, will it produce an integer? It can be seen that A plus B, which is an integer, will provide C. This C is also definitely an integer. It's just a statement. It's just a properties that you need to mention anyway. This is the statement is the answer already. It's the explanation. A plus B will always be an integer. This is what it means. My conclusion is that G is closed. That's all. Number 2 also quite similar, but involves 3 elements. If you have 3 elements A, B, C, which is an integer, try to picture this. A plus B plus C, you add up the first bracket. We will open the bracket. A plus B plus C, it will also be similar with this. This is also the same properties. The left hand side is equal to the right hand side. The binary operation is plus, the element is integers. I just conclude that G is associative as well. Try to proceed with the next one. Identity. I take an integer A. The question, does there exist some identity such that this happens? A plus E equals to E plus A, you get back A. And that E must also be an element of integer. Remember, this must be applicable for every integer A. You don't really put 1 plus something equals to something plus 1 equals to 1. You cannot do that. Remember from the previous video lecture, to conclude for every, it must be in a general variable. Try to imagine, suppose that E must also be an integer. What is there exist? A plus E equals to E plus A, you get back A. What is the value of E? For the existential thing, there exists identity. You must specifically state what is the E. But again, that is applicable for every integer. In this case, for the binary operation of plus for addition of integer, the E is 0. It exists because you take any integer, A plus 0 is equivalent with 0 plus A, you get back A. The identity exists and the identity is 0. And 0 is also an integer. There exists an entity. Which is 0. Okay, we proceed to the next one, which is associative. This one might be a little bit tricky. For every A in Z, A plus the inverse of A plus A. Right now we have the identity, it must be equivalent to 0. Try to picture this. What is A plus A inverse equals to A inverse plus A equals to 0? The A inverse will be negative A itself. This is my showing of proof because A plus negative A equals to negative A plus A, which is equivalent to 0. Therefore, if we put the example in practice, what is the inverse of 1? The inverse of 1 is negative 1 because 1 plus negative 1 is equal to negative 1 plus 1 is equal to 0 as well. How about if we put A equals to 2? Remember, this is not the proof, it's just as an example to show that the top statement, the top general statement is true. If I put A equals to 5, what will be the inverse of 5? The inverse of 5 is negative 5. Because 5 plus negative 5 is equals to negative 5 plus 5 is equal to the identity of the addition of integer, which is 0. Just now, I just showed that the addition of integer is closed. It is associative. There exists identity which is 0. There exists the inverse for every A, which is negative A itself. As a large conclusion is that the given G which is the addition of integer is a group. Right now, we already understand there are 4 characteristics Why not I add one more, but it is at the future of the subtopic, but I think it's better for me to say it right now, is that abelian group. You can look at the future slide, but there's a reason why I include it. It's better to understand. Abelian group is a group, therefore it must be closed, it must be associative, it must have identity. I will not write the general full definition of this characteristic because we just mentioned it just now. It must have inverse. But the thing that differs from abelian group with a normal group, it is commutative. And commutative means for every element of the G, A binary operation B is equal with B binary operation A. Very simple. And let's take an intellectual exercise here. Is the addition of integer is an abelian group as well? We just proved that it satisfies characteristic 1 until 4. Right now for the commutative part, for the addition of integer, you take two integers A and also B. A plus B is equals to B plus A or not? You take two integers A, B, A plus B, is it equals to B plus A for every integers? And the answer is yes. Definitely. The addition of integer is commutative. If I want to include the previous solution, Z plus is an abelian group as well. Abelian group, the name from the famous mathematician Neil Abel, I don't remember, comes from his name because he suggests that the ring structure must also include the commutative. We already at the first example, finished at the first example. Some of the things that you can conclude right now is that the study of abstract algebra is about the properties of any set and any binary structure, and we need to investigate whether it satisfies certain characteristics or not. Why not I proceed with the next, a simple one, which is the subtraction of integer. And the question, is it an abelian group, or even we can start, is it a group? And if is it a group, is it an abelian group? Subtraction of integer. Let's start with the first one, closed. And if I want to transfer into the notation, you take two elements from Z. The question, A minus B will produce some element C. If A and B is integer minus integer, will it be another integer? In this case, C is an integer as well. My conclusion is that this G is closed, definitely. The properties, integer minus integer is integer. Associative. Is it associative? I take A, B, C, which is integer. The question first, A minus B minus C, is it equivalent with this? It does not equal. Left hand side and right hand side is not equal. I want to prove by counter example to show that it is not equal. Counter example, you can use example. Yes, for example like this, a equals to 1, I take b equals to 2. You can take any valid integers. I do the left hand side first. 1 minus 2, then I minus 3. It will be equal to 1 minus 2, negative 1, negative 1 minus 3, it becomes negative 4. If I do 1 minus 2 minus 3 first, 2 minus 3 is negative 1, 1 minus negative 1 will be 2. Let me double check. 1 minus negative 2, negative 1, negative 3, negative 4. 1 minus 2, negative 3, 1 is 2. I conclude right now is that 1 minus 2 minus 3 is not equal to this. And I can conclude right now is that this G, which is the subtraction of integer, is not associative. Now we come to the third characteristic, which is identity. For every a that exists identity which is also an integer such that this happen, a minus e equals to e minus a, you get back a. Some of you may say that the value of e is 0. Let's try it. Is it true? You take 1, or you can take a, by the way. A, suppose that e equals to 0, yeah? A minus 0, is it equal with 0 minus a, which will get back a? The answer is no, because a minus 0, you get back a. 0 minus a is not equal to a. I can say it in this way, or you can say that 0 minus a is not equivalent to a, because this is a wrong case. Or you can use counter example. Sometimes it's much easier for you to write counter example like this. You sometimes might not use a, but if you use a also can in the general term. But if counter example, I simply can say let a equals to 1, let e equals to 0. 1 minus 0 is not equivalent with 0 minus 1, which is not equivalent to 1 itself. Basically, is there any integer which satisfies this equation? You can try to put e equals to 1, but maintain a equals to 1. If a equals to 1 and e equals to 1, what will happen? 1 minus 1 equals to 1 minus 1 this time. You get left hand side equals to right hand side. But the problem is that you will not get 1. You must get back 1. As 1 minus 1 equals to 0, you don't get a equals to 1. Actually, for the identity, you cannot prove directly in a simple mathematical proof is that there does not exist identity. You can try, but I simply can say like these properties is that there does not exist identity which is an integer such that a minus e equals to e minus a, you get back a for every integer, no space, for every integer. That's all. You can conclude with G has no identity. As simple as that. And because G has no identity, and it will affect the inverse statement as well, because inverse is like this. Suppose for every a, which is an integer, there must exist the inverse in the integer such that a minus inverse equals to inverse minus a you get back identity. But the problem is that there is no identity, therefore this part is not applicable. The best way for you to conclude is that as G has no identity, inverse also not exists. You can say it as your conclusion. We finish by proving is that by checking all the properties is that this subtraction of integer is not, definitely is not a group, because it does not have it is not associative, there is no identity, and there is no inverse, although it is closed. Let's try to directly show whether it is a commutative or not. I want to determine whether it is an abelian group by checking all the properties of abelian group. For every two integers, the question is a minus b equals to b minus a. Based on our previous experience at associative, definitely you can see I can take a equals to 1, b equals to 2. 1 minus 2 equals to negative 1, 2 minus 1 equals to 1. Definitely negative 1 is not equals to 1, 1 minus 2 is not equals to 2 minus 1, and again G is not commutative. The subtraction of integer is not commutative. I just proved two questions at one spot at the same time, at one move, which is that subtraction of integer is not a group, and it's also not an abelian group by checking all the properties of group and abelian group. In this video will be quite long if I continue. I will stop here and I will proceed with the next video lecture, which includes the set of Zn, which it means integer modulo n. That's all for the first video. Thank you.